Hello everybody. Today I will continue on electromagnetic course. In previous lectures we were speaking about the vector analysis, how we can we give some coordinates, some operators in vector analysis that is very useful in the electromagnetic calculation, the mathematical representation. Today we'll start in the first thing in related to the electromagnetic, the electrostatics. So starting with what is the meaning by a charge. So a charge is a property of matter, of the material that you have, and there is negative and positive charge, and we can measure it in coulombs. Okay, so coulombs law, this is the scientist that make some experiments and measure the force between two charged bodies. There is a displacement between these two charged bodies, and he made some experiment to measure this force and to know what is the parameters that affect the charge in one body and how it affecting another body, for example a cubic material, or a cubic rod, or rod of meter rod. For example, 2 meter rods, we charge it, there is a big positive and negative charge. So he in conclude he have the following results, that the charge between the force between the charged body vary directly with the magnitude of its charge. If the charge have a higher magnitude, then the force is higher. It vary inverse with the distance. This is obvious if you put both material be near to each other. It is having, both of them having a higher effect at the other one than if they are far away. So if you put the body A and body B at 1 centimeter, it is different if you put it at 1 meter. And he find that when the distance is very large, then the force is very small. It's very inversely with the square of the distance. Can be only, or the force have a vector, a direction. So the direction is on the line joining the charge. So the charge have a line. You can draw a line between both of them, and this is the direction of the force. And he said that it is attractive or repulsive depending on if the bodies were oppositely charged or have the same type of charge, positive and negative, or both of them are positive or both of them are negative. Okay, so he concluded mathematically to this expression, the force of the charge 1, Q1, affecting Q2. So the direction is from Q1 to Q2, and they are in the free space related. This is R1 and R2 related to the origin 0, 0, 0. So this is the force. It is inversely to R squared, the distance between both of them, and proportional to the Q1 and Q2, and this is the direction from R1, from 1 to 2, and this is just E epsilon 0 multiplied by a number 4 pi. This is just a constant. Okay, so the epsilon 0, it is related or depending on the material, or the material in between the charges. So here, if we put the charge in the free space, then we have epsilon 0 equal to this number, Of course it will be different if there is different medium or different different material between the charges here. Okay, so Q1 and Q2 is the charge, R is the distance measured in meters, F is the force and measured in Newton, and epsilon 0 has the unit force over meter. Okay, now consider again the law of Coulomb's, but take the Q2 out of this quantity, or out of this vector here, because we have a direction and we have a value. So this is the effect of Q1, and this is the absolute value for the charge Q2. So this is all of them related to Q1, relate du Q1, and this is a property of Q1 independent of the Q2. So Q2 may be changed, but this is different. Okay, so this is related to Q1. This is the force coming from the charge 1 to charge 2. Okay, so now imagine that there is no force here, there is no other charge Q2. So if we remove Q2, if there is no other charge, this force is still available. So Q1 have its force, or have its exist. The electric field of Q1 still exists. So we denote this one only as the electric field. Okay, electric field intensity. So it is volt over meter, this value, and so we can write F as Q2E. Okay, E and E, this is a vector. Okay, so consider, instead of one charge, instead of Q2, consider multiple points. Consider it as a sphere, for example, or around Q1, and there is many points, n points around it. So we can write the distance R from R to R1 here, R1, R, R2. So this is R1, R2. So you can make the difference here to get R1, 2. So consider this endpoint. So you just take the summation, the effect from Q. This is the total force here. Here, that this is the hold for the total force acting on test charge Qt. Okay, so we have here the not all of them, all this charge affecting Qt. Okay, so all of this charge, we take the summation over the value of this charge from Q1 to Q2, Q3 until Qn, and the distance. Okay, so here we have the value of F, the force of many n charges affecting Qt. Okay, now, and R1 until Rn is the vectors from the origin to point charges Q1, Q2, and Q until Qn. Okay, so E is just, you will remove Qt, and you still have all of the other other charges emitting, or the field, electric field still exists, even if there is no test from them. Now let's see another thing. If I have a large amount of discrete charges, n charges, in a free region of space, so we can define a charge density, volume per charge, or charge per volume, as the difference here in charge over the volume. So we name this as rho v. So we put some charges in volume, for example, as sphere or cubic, cylindrical. So all of these charges over the volume, we name it as the charge density, or volume charge density. Okay, now take the total charge in this region, if we take a small value of this and this, then if you take the integration, you calculate all the charge, the total charge in this region. Maybe imagine that this region is a part of a wire, and you want to measure all the electric charges in this wire. So you take a very small part, and the wire, if you know, the wire is cylindrical, have a small, of course it have a very small area and a length. So we take integration over rho v delta v, so we can have some information about what is the charge here. Okay, now if the charge is distributed in a surface here, if that we assume that charge is distributed in a volume. Okay, now if the charge is distributed on a surface S, now the charge is distributed in a very thin layer, or for example the static charge, that's if you have a ruler and you may make it move slowly over your hair, then this is a very basic experimental. Then you will have some charges, very small charge in the surface of the ruler, because this is dielectric material, so you have a static charge in the surface of this ruler. So this is an example that you can have a charge on a surface, you can have a charge in a volume. So the surface charge density is defined as delta Q over delta S, a very small charge in a very small part of the surface, equal rho S. Now calculate the over the total surface Q. You will have the Q, the total charge in this case will be the integration over rho S ds. Okay, if it is on a line, a very thin line that connecting a point to a point, this is not a surface, not a volume, then you will see that is delta Q delta L, a small displacement of this line. And if you take the integration, then you will calculate all the charges in this line to get Q. Okay, this is just equations for the charge. Okay, the Q. Now let's take this Q in volume, in line, in surface, and put it in E, our E, electric field intensity. Remember that due to rho L, rho S, rho V, then you will put it instead of the rho S, rho L, instead of the Q over the R, and you will take the integration over dl, ds, dv. You will get your E. And of course, if you multiply by a QT here, a Q, another Q, then you will get the force. Okay, R is the positive vector from the origin to the observation point, and this is a very small definitions. We here didn't, of course, I didn't prove some equation, but I give you some basic mathematical definitions in electrostatics. Okay, let's move to another thing here. We will take the first equation of Maxwell equation. There is 4 Maxwell equation in electromagnetic. This is the most important 4 equation of Maxwell that they define it to define the electromagnetic field. Okay, first one is Gaussian Law, Maxwell's equation. This is he state that if you have a space, if you have a surface, let's say that you have a surface see, let's here, yeah, and yes. So if I have a surface here, as this surface may be like this, and this surface have some charge like I said here in this surface, okay, this charge in this surface I can't yes, so the total charge enclosed in this surface divided by epsilon 0, okay, Gauss law is said that this total charge enclosed in this surface, okay, so you take the calculation of the Q that we calculated before, it's equal to the electrical field intensity. It equal to all the electrical field that come across this surface, okay. That is the meaning of the charge of the Gaussian law, okay. So let's see here, he said that Q over epsilon 0 equal phi. Phi is the total flux, and it is equal to the integration over this surface, the total flux. So he said that the total flux of the electric field intensity that come across over this closed surface is equal to the total charge enclosed in this surface. So this is equal to the integration in closed integration over E dot ds, okay. So integral form of Gaussian law, it is like this. You take the equality, this equal this, okay. This is very easy. So Q enclosed is the total charge contained here, bounded by the surface, bounded the boundaries of the surface. And if we apply the divergence theorem from before, the enclosed surface here dot S is equal to the divergence of E dot delta V. This is from divergence theorem. So if this is the enclosed surface is equal to Q over epsilon 0. So again, if after applying the divergence, again equal to Q over epsilon 0. If we remove Q over epsilon 0, if we remove Q and take the integration over the volume, the rho V delta V, then we have integration over the volume and integration over the volume, so we can remove both of them, and we have rho V over epsilon 0 equal to divergence of E. So this is meaning that the divergence of the electric field intensity is equal to the charge in the volume over the epsilon 0. Now electric flux density, so it's dependent on the medium in which the charge is placed, okay. So we can define another thing, epsilon 0 multiplied by E, we can define it as D dash is the flux of D, okay. So the this vector known as the electric flux density vector, okay, or displacement vector. So the electric flux, the unit of electric flux is measured as the coulombs per meter square. So it is C over M square, okay. The electric flux density is C over M square, and the electric flux is coulombs, okay, because the electric flux is the charge in this surface, or the charge contained, okay. So it is equal to the charge. Now let's see here the divergence of D. This is very easy. If you multiply, take this one and multiply it by the divergence of E, multiplied by the E. This is an absolute value that is related to the material. So this is what we take epsilon E as we name it as D. Okay, so divergence of D equal to rho V. This is the Gaussian law again, can be written again. So this is the first of the four Maxwell equation, as I said, and this is stated that the divergence of electric flux density is equal to the volume charge density. What is that meaning? That again, the total charge in the volume, in this volume closed by a surface, is equal to all the electric charge field, the electric field that come across. So if imagine the field as lines and imagine the charge as points, all the number of points inside this cubic or inside this volume is equal to all the lines that come from this box or this sphere. Okay, so Gaussian law is the alternative statement of the Coulomb's law, proved an easy finding of E and D for symmetrical charge distribution. So all the charge distribution come symmetrically, and there is no intense in some places, and some places that doesn't have lower charge than another. Okay, so this is what I said today. This one is very important, and this one is very very important. This is the integral form, and this is the differential form of the Gaussian law. Okay, this is for today. Thank you for listening.